This is a video for AQA Further Pure, second order differential equations 1, homogeneous equations, 1.7, auxiliary equation with complex roots. So again, for this general second order differential equation with this auxiliary equation, if the discriminant is less than 0 and b is non-zero, I'm going to get roots to the auxiliary equation of the form alpha plus or minus beta I. So how does that affect the general solution? I'm going to get that y is equal to a e to the alpha plus beta I x plus b e to the alpha minus beta I x. Well, I can take out a factor of e to the alpha x, so I'm going to get e to the alpha x times a e to the beta I x plus b e to the minus beta I x. And we've already seen that this thing can be written in terms of coses and sines, so I'm going to get a general solution that is e to the alpha x times p cos beta x plus q sine beta x. So there's that written up for you to follow a bit more easily. There are my roots to the auxiliary equation, and down here is my form for the general solution. And remember, it's important to know where this has come from, but you don't need to derive it every time you do a differential equation of this sort. So looking at an example then, let's have a look at this differential equation. I've got an auxiliary equation for this, which is just m squared plus 2m plus 17 is equal to 0. And using the quadratic formula on this, I'm going to get that m is equal to minus 2 plus or minus the square root of 4 minus 68 all over 2. And that gives me minus 2 plus or minus the square root of minus 64 all over 2, which gives me minus 1 plus or minus 4i. So my general solution is going to be y is equal to e to the minus x p cos 4x plus q sine 4x. And again, there's that a bit more tidily. There's my auxiliary equation and my roots of the auxiliary equation, and then finally my general solution. Now, in a previous video we looked at this form and decided that that could be written as r sine 4x plus alpha for some value of r and alpha determined from the values of p and q. So this thing is really e to the minus x times that, and we're going to have a look at a plot of this on the next slide. Okay, so there's a plot of that function. Two different sets of values for p and q, 1 and 1 here and 5 and 14 here. Very similar looking plots. And on the previous slide I suggested that actually this could be written as y is equal to r e to the minus x sine of 4x plus alpha. And if I look at these two plots here, this curve here, the blue dotted line, is actually r e to the minus x. And so what's happening is that this red line, the plot itself, is an oscillating function. It's a sine type function oscillating with a frequency of 4. And its oscillating within the confines of this re to the minus x function. Let's have a look at a dynamic plot for that. So as I alter the values of p and q, I know that in fact all I'm going to alter is alpha and r. So as I alter the values of p and q, you can see that it still oscillates 4 times. We've got here, let me just drop that down a touch, sorry. So we've got here 1, 2, 3, 4 troughs within the range minus pi to pi. And that suggests that it's oscillating 4 times over a 2 pi range. And it's staying within the confines of this blue curve. And you can see up here, because e to the minus x tends to 0, the oscillation between that curve actually gets smaller and smaller. And this is an example of a damped oscillation. That was the final video in this sequence, second order differential equations 1, homogeneous equations.